Have you ever been at an airport, looked out at one of those massive jets, and just wondered, how in the world does that thing get off the ground? Well, today, we're diving deep into the heart of the machine. We're talking about the incredible engines that make flight possible, from the smallest propeller planes to the biggest airliners. And let's just jump right in. Look at this. What you're seeing here is a cutaway of a J85 turbojet engine. I mean, it's just a beautiful piece of engineering, isn't it? It's made of thousands of individual parts, all working together perfectly to create an unbelievable amount of power. This is the kind of engine that gets a fighter jet screaming through the sky. It really is an amazing feat of physics and engineering. So how does a complex machine like this actually work? How does it generate enough force to lift a huge, heavy aircraft off the runway and push it through the air at hundreds of miles per hour? That is the big question we're going to tackle today. Okay, so to answer that, we really need to understand that there are basically two different ways to create thrust. You can think of them as the two main families of aircraft engines. So on one side, you have what we can call action engines. These are your classic propellers. The idea is simple. They grab a whole bunch of air and just throw it backwards. But on the other side, you've got reaction engines. Yep, we're talking about jets. They don't really push the air. Instead, they actually push themselves forward. And we're going to see exactly how they pull that off in just a minute. Let's start with a classic, the piston engine. And you know what? If you have a basic idea of how a car engine works, you're already halfway there. This is the tech that powers most small aircraft and, literally, got the whole field of aviation off the ground. All right, let's break down the main parts you're looking at right here. You've got this cylinder, and inside it, a piston that moves up and down. You see those valves? Those let air in and exhaust out. And of course, the spark plug for the ignition. All of this is connected to a crankshaft, and that's the really crucial part that turns the piston's simple up and down motion into the spinning force that turns the propeller. So this all happens in a super fast four-step dance. Step 1 is intake. A valve pops open, the piston drops down, and a mix of fuel and air gets sucked right into the cylinder. Then comes step 2, compression. Both of those valves slam shut. The piston rockets back up, squeezing that fuel-air mixture really, really tight. It's basically packing it full of explosive potential energy. And now for the good part, the power. The spark plug fires, igniting that compressed mixture and creating a powerful, controlled explosion. That blast forces the piston down with incredible force. This right here is the power stroke, and that's what turns the crankshaft and ultimately spins the propeller. And finally, step 4, exhaust. Another valve opens up, the piston rises one more time, and it pushes all those spent gases out. And get this entire four-stroke cycle happens thousands of times every single minute. Now, piston engines are absolutely brilliant, but they do have their limits. To go faster and fly higher, engineers had to turn to a totally different principle of physics, one that would completely change air travel as we know it. And that new principle is all about action and reaction. Remember how propellers work by pushing a bunch of air backward? Well, jet engines do the exact opposite. They shoot a high-speed jet of gas out the back. That's the action. And the reaction to that is what pushes the engine and the entire plane forward. This is pure classic Sir Isaac Newton's third law of motion. You know, the easiest way to feel this for yourself? Blow up a balloon, but don't tie it. Just let it go. As the air rushes out the back, that's the action. The balloon zips all over the room. That's the equal and opposite reaction. A jet engine is really just a much, much more powerful and controlled version of that same idea. So this basic action-reaction idea has actually evolved into a whole family of different jet engines. Each one is designed for a very specific job. So let's take a quick look at this family tree. First up, we have the turboprop. Now, this one is a really clever hybrid. It uses a small jet engine, a gas turbine, but not for direct thrust. Instead, it harnesses all that power to spin a traditional propeller through a gearbox. This makes it super efficient for shorter flights at lower altitudes. But propellers have a problem. They have a speed limit. As a plane gets close to the speed of sound, what we call Mach 1, the tips of the propeller can actually start spinning faster than sound itself. This creates shock waves and a massive amount of drag. So to go any faster, aviation had to ditch the propeller completely. And that's where the turbojet comes in. This is the purest, simplest form of a jet engine. It just sucks air in the front, squeezes it, mixes it with fuel, and lights it on fire, and then blasts the exhaust out the back. It's simple, it's brutally powerful, and it is built for one thing: pure speed. And finally, we get to the engine that powers pretty much every modern airliner you've ever flown on, the turbofan. Now look closely at this diagram. You see a little bit of air goes through the hot engine core, just like in a turbojet. But see that giant fan at the front? It pushes a massive amount of cold air around the core. And here's the crazy part. That bypassed cold air generates about 80% of the engine's total thrust. It turns out it's way more fuel efficient to move a huge amount of air slowly than a small amount of air super fast. That is the secret to modern air travel. So think about that journey. We've gone from the mechanical push of a piston spinning a prop to the elegant, powerful reaction of a high bypass turbofan. It's just a remarkable story of how technology evolves. And this side-by-side comparison really says it all, doesn't it? On the left, you've got the beautiful mechanical simplicity of the piston engine, and on the right, the incredible complexity and power of the modern turbofan. Both get a plane into the air, but they represent two completely different eras of human ingenuity. What a remarkable journey of innovation, right? And it really leaves us with one last big question. As we keep pushing the boundaries, looking at things like electric propulsion or even ramjets, what kind of engine do you think will power the airplanes of tomorrow? Thanks for diving into this with me.